And so once again we have an incredible discovery from the James Webb Space Telescope. This time another record. A record from the absolute edge of the observable universe, with the light once again taking billions and billions of years to reach us. And as the title of this video suggests, it's really about the most distant supernova we've ever seen. And in this case, this is a pretty important discovery because it does actually tell us a little bit more about the early cosmos, and of course why these particular supernovae are so essential for our existence right here on planet Earth. And so let's talk about this new discovery in a little bit more detail, but I guess let's start with just a little bit of an overview and some of the previous record holders from the last few decades. And once again, let's start right here. This is the timeline of the universe. The universe is estimated to be approximately 13.8 billion years. And the majority of supernovae actually happened around this time. This is often referred to as the cosmic noon. Mostly because the universe was at its brightest, contained the most stars, the most supernova, and the most light coming from everywhere. This was about 2 to 3 billion years after the Big Bang. And since then, as we discussed in some of the previous videos, the universe has been getting darker and darker, colder and colder. But obviously supernova happened before this as well. But scientists are not entirely certain how exactly they differed back then compared to what we have today, especially because the stars back then were actually kind of different. Although I guess a quick side note, when we say supernova, we actually talk about a very large umbrella of very similar but somewhat different events that essentially do involve exploding stars, but the reason for that explosion and the actual mechanism involved can be entirely different. And normally it involves one of two primary types. Type1A supernova involves a white dwarf that reaches a certain mass limit, referred to as the Chandrasekhar limit, and basically explodes because it can no longer sustain itself. Whereas the Type 2 supernova involves a collapsing massive star that bounces back following the collapse, with all of this gas exploding all at once. And so some of these events that happened billions and billions of years ago essentially had their light redshifted as a result of the universe's expansion, with most of this previously visible light now becoming infrared, which is why quite a few of these events should be pretty easily visible to the James Webb, the most sensitive infrared telescope we have in operation. And not surprisingly, it did discover quite a few that we're going to be discussing in a few minutes. But why exactly is this so important? Well, for once, because if stars did not explode, life as we know it would not be possible. Pretty much everything inside of you and me, everything from iron in our blood to silicons that we use for basically computer stuff and watching YouTube, are forged in the course of these massive stars, with all of these elements being released when they go supernova. And so, because of these events, a lot of different objects out there, including planet Earth, were eventually enriched with a lot of heavier elements, allowing for things like life to eventually evolve. But most of our knowledge of supernova comes from neighboring events, and specifically from stars that are maybe not so different from what we find in the Milky Way galaxy, and stars containing a lot of heavier elements and a lot of remixed material from previous supernova, and not the pristine material from the beginning of the universe. And so for years, astronomers have actually been trying to find some of these most distant supernova in order to find out what kind of differences they might contain, and to figure out how all of this enrichment process actually started. And one major discovery here was DESY 16C2NM. This was actually discovered by the Dark Energy Survey, whose actual purpose was to try to map a lot of different galaxies in order to study the dark energy, with this being discovered completely by accident. Here, the light traveled for approximately 10.5 billion years, and at the time of the discovery in 2016, this was essentially one of the oldest supernovas studied. It actually belonged to a class of unusual supernova referred to as superluminous supernova, which represents some of the brightest and the rarest explosive events in the entire universe. And so here, by studying things like, for example, ultraviolet emissions, scientists could finally understand the amount of metals produced in the explosion and the overall temperature of the event, comparing it to some of the modern supernova we have today. But even back then, this was not the record holder, and instead it was this. SN 1000 plus 0216 that was discovered back in 2012 and was found at a redshift of 3.9. Or the light here took approximately 12.1 billion years to reach us and traveled a distance of about 23.6 billion light years. And so this actually stayed as a record holder for at least 12 years. And it was really these earlier studies that finally established a way for us to look for these supernovae, because previously it was a little bit challenging to find, and scientists were not entirely sure how to even look for them, despite these objects being super bright. But pretty much everything changed with the arrival of the James Webb Space Telescope, because here it did not take long to find even more at relatively similar distances. As a matter of fact, some of the earlier teams using the data from the James Webb identified 10 times more distant supernova compared to what was previously available from even surveys like DESY or the observations from Hubble Space Telescope, with many of these discovered when the universe was only about 2 billion years old, so essentially 11.8 billion years ago. And among these discoveries, a particular type of supernova was especially intriguing, a Type 1A supernova. Once again, this is the one involving a white dwarf, so basically something that our Sun is going to become one day, exploding when it reaches the mass of about 1.4 solar masses. This usually happens as a result of consuming mass from its partner, or possibly some kind of a collision. But here they're also important for another reason. They're often referred to as the standard candles, or essentially because they produce relatively similar brightness, they can then be used to determine distances, even if they're super far away. And so their main use today is measuring vast cosmic distances and helping scientists calculate the universe's expansion rate, which is currently believed to be the result of the dark energy, whatever that is. Even today nobody actually knows. And so here one of the most recent groundbreaking discoveries was this, AT2023 DESY. This was at a redshift of 2.9 and was definitely a Type 1A supernova. So this was about 11.5 billion years ago. And this discovery was important because it actually reinforces a crucial constraint in cosmology when it comes to the formation of different stars and when it comes to understanding how we think the universe very likely evolved. Today scientists predict that Type 1A supernova should not be actually happening in galaxies at much higher redshift than 4. Mostly because we don't really think white dwarfs that possibly existed back then would be old enough to explode yet, and thus it should not be technically possible to see any of these events yet. And so if actually one day we do see an extremely distant Type 1A supernova, this will definitely break cosmology. But finding this supernova at the redshift of 2.9 confirms the limits and the prevailing mathematical models, and of course the famous Big Bang theory. It essentially demonstrates that a lot of these massive stars do require sufficient time to form and to evolve, and to then collect enough mass to produce Type 1A supernova. But now we have something else. So let's talk about this most recent discovery that's once again breaking records. And it's the event you see right here. Although in this case, as you can see from the name, this is known as the GRB or E-gamma ray burst. You can learn a little bit more about these events in one of the videos in the description. But this GRB definitely produced a supernova and was definitely a result of a massive collapsing star. And surprisingly, seems to have happened approximately 720 million years following the Big Bang. So essentially over 13 billion years ago, at an incredible redshift of 7.3, as reported in a study in the description. There are actually 2 studies about this from slightly different teams, and they both report the same thing. And while in this case, this breaks previous records by approximately 1.1 billion years. So this happened much earlier, and is definitely super exciting. But as you can see from this image, it's also barely visible. But what exactly was this, and what do we know so far? Well, this was a long-duration gamma ray burst. Basically a very violent explosion associated with the core collapse of a very massive star that then releases huge amounts of gamma rays, producing 2 powerful jets in opposite directions. And here it was really the follow-up observations that finally confirmed the existence of this event and its distance. And that's due to the expansion of the universe that actually stretches the timing of the event and usually causes the supernova's peak brightness to be observable months after the initial gamma ray burst detection. And that's because these jets, as they travel away from the source, they basically start interacting with a lot of additional matter, and then start producing different emissions in different wavelengths and with different brightness. But here, as always, there was a bit of a surprise. This ancient supernova, despite its age, looked exactly like the modern supernova. There was basically practically no difference in terms of emissions. For example, here this was compared to the much closer SN 1998 BW supernova that also involved a gamma ray burst, and they literally look almost identical. And that's actually a really important confirmation for a lot of different modern cosmological models. And so here, even though this is a really ancient event that took place during the epoch of reionization, when a lot of hydrogen gas was still neutral and was actually blocking some of the light from passing, the actual explosions producing some of this light seem to have followed exactly the same mechanism as they do today. And here this provides an answer for a previously unanswered question. Scientists have long wondered if some of these earliest stars and galaxies differed substantially from those that came later. For example, in terms of mass, size, density, composition, and so on. Mostly because they obviously contained much more pristine and much more primitive elemental gas. But by finding a star exploding 720 million years following the Big Bang, and a star that exhibits very similar properties to modern supernova, suggests that at least some of these massive stars during the first billion years were very likely extremely similar. Which is also a very important confirmation of the so-called cosmological principle. The universe more or less seems to have very similar physics, no matter when we look. And at the same time, this also constrains theories about the brightness and mass of these early explosions, implying that their brightness was actually also very similar. They were not much brighter as some scientists previously speculated. And so here we have a very powerful physical confirmation that fundamental physics governing stellar explosions was already established back then, even when the universe was extremely young. And so here, based on the observations of these several supernovae from different time frames, we essentially have many different confirmations for the foundation of modern physics, and specifically the foundations for cosmological models used to explain a lot of other phenomena. And so here, every distant supernova we find provides a new data point, which then helps astronomers piece together a more complete and factual picture of how a lot of complexity around us seems to have arisen from very simple pristine gas in the extremely early universe, which eventually led to the universe we live in today and, of course, our own existence. But at least for now, that's really all we know. This is definitely a super exciting discovery, but until future observations and future studies, we're not going to know much more. And so once we learn something else, we'll discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt with the JWST as one of the designs. Stay wonderful, I'll see you tomorrow, and as always, bye bye.